We have already talked a little bit about chi-square testing for goodness of fit. Today we are going to talk about chi-square testing for both single and multiple populations, and we are going to use two-way tables instead of one-way tables. So today's title of our notes, I guess, are Inference for two-way tables. The first type of chi-square testing we're going to talk about today is called chi-square test of independence. The purpose of this test is to test if there is any independence or association between a variable in a two-way table for a single population. So this can be in a simple random sample, or it can be done in a single population that's in some kind of experiment. But either way, we are looking for different associations within the variables and your population. Our null hypothesis will always be that there is no association. We are assuming that they are independent of each other. Our alternative is that there is an association or that they are dependent. And so sometimes we will write this as there is no association. Other times people will say there's an association. Or, since this is called the test of independence, a lot of times we will say that the variables are independent or dependent, but of course everything is always in context. These are just very brief versions of our null and alternative hypotheses, but remember, we will always write them in terms of context. So the conditions for the chi-square test of independence is the same as before. That's kind of nice. We've already done these before. You have to have a single random sample, or the population in a sense of some kind of randomized experiment. The expected values all have to be greater than 5, and then you're going to check for independence if you're sampling without replacement, but if it's an experiment, then you're good to go. So let's look at number 4 in your packet for inference for categorical data. You got this the other day in class. We've already done 1 through 3 together. Now we're on number 4. So I'm going to give you a second to read this, and then so go ahead and pause it and then come back. We have a table here of deployed versus not deployed U.S. military personnel, and we are looking at the different causes of death, and we are trying to find, is there an association between cause of death and whether or not they were deployed or not deployed. And our population of interest would be the U.S. military. So we've got this ginormous table here. We've got 2 different rows, 3 different columns of stuff. So 6 different possible categories. So you've got unintentional deployed, illness deployed, homicide deployed, and the same thing for not deployed. So we are testing at the 5% significance level that the claim of the cause of a non-combat death is independent whether the military person was deployed in a combat zone. Okay, and I know that this is going to be a chi-square test of independence as opposed to a chi-square test goodness of fit, because I have one population but multiple categories for my population. So because this is no longer a one-way table, but this is a two-way table, I have deployed versus not deployed on this side, and I have multiple causes of death. This is what we consider a two-way table. So if you see a two-way table, you cannot use a goodness of fit test. If you have multiple populations within your two-way table, that is a different kind of test we're going to talk about here in a little bit. So we're going to do a chi-square test of independence. My null hypothesis is that the deployment status and cause of death are independent. So my alternative hypothesis is that deployment status and cause of death are dependent. The next thing I'm going to do before I even continue is I have to see if my expected counts are high enough for me to be able to use this test. So I have my table, which again, this is already on your paper. We're going to put our expected values. You can put them in a separate table in your notes, or you can put them in a space right here. I'm going to show you a whole new table, but you put them wherever you need to put them. So how do we come up with expected values if we have so many categories going on? So what we need to ask ourselves is, what are we expecting to be true about the table? And what we're expecting is that they are independent. Like, we are expecting that deployment status does not have anything to do with cause of death. That is our assumption. Okay, they are independent. So if that was truly the case, okay, if deployment status and cause of death are independent, then the probability of A and B, the probability of someone being deployed and the probability of any type of cause of death If they are truly independent, this right here is equal to those two probabilities multiplied together. Okay, this was from way back at the beginning of the year. You might need to go back and check some of that stuff, but if two probabilities are independent, the probability of A and B occurring is simply the probability of A times the probability of B. Let's look at one specific example in this table. So let's look at the probability of deployment and also dying of illness. To do any of these expected values, I'm going to need to find some totals. So I'm going to find all my total values for the entire table. I'm going to add these two together, my unintentional injury. I'm going to add illnesses together, homicide or suicide, and then I'm also going to add across. So all of my totals here are coming. Hang on one second. There they are. There's my totals. So I have a total of 1,580 people in my sample. Okay. So to determine the probability of deployment and illness, I'm going to simply find the probability that they were deployed multiplied by the probability that they had an illness. To do that, I look at the totals from my table. The probability of someone being deployed, okay, I look at, out of my total population of 1,580 people, I have 224 people that were deployed. You're asking, where did I get that number? These are all the people that were deployed, and there's the total. 224 out of 1,580. So the probability of someone being deployed is this number right here. The probability of someone having an illness is going to be the total number of people in this column, which is going to be 294. So that's going to be 294 out of 1,580 total people in my sample. So these are the separate probabilities for deployment and illness. To find the probability of deployment and illness, remember, we are just going to multiply these two probabilities together. So 224 over 1580, that one comes from there. This one comes from here. I multiply those together and I get 0.02638. So if someone is both deployed, the probability that someone is both deployed and dies of an illness is 0.02638. That is out of my entire population. So I'm going to take this number and multiply that by the entire population. Okay? So, if there are 1,580 troops, how many would we expect to be both deployed and die? 0.026 of them. Or like the probability is 0.02638. So I'm going to multiply that by 1,580. That's going to give me my expected deployment and illness, die of illness, which is 41.681. So this number right here will go right here, 0.681. That is my expected. And you can round to 2 decimal places. I just wrote 3. That's fine. Just remember that you cannot round to the nearest whole number. You must have at least 1 or 2 decimal places. You must have 2 decimal places. If it's there, sometimes it'll round to a whole number. But if there's a decimal, 2 places is good. Okay? Another way to look at this, your expected count is simply to take 224 out of 1580, 294 out of 15, times 290 out of 1584, and then you're going to end up multiplying by 1580. Those two cancel out. So another way to think of this is to take 224, sorry, this is a new table, but 224 is a row total, 294 is a column total, 1580 is the grand total. So you could multiply your row total times your column total over your total or grand total, and that will also give you your expected count. So here's our formula. Here we go. There's the animation. Row total, column total, grand total, and that gives you your expected count. So you're going to want to write this down. Expected count is equal to your row total times your column total over your table total. If that's confusing for you, go back a slide or a couple of slides, go back a little bit, look at how we found the specific example for deployment and illness for this category right here, and hopefully that'll make a little bit more sense. But I'm going to repeat that process, not on this video, but I'm going to repeat that process for every other category, the other 5, and I'll have those totals up next. So if you need to, pause it, calculate those on your own, and make sure you get the same thing I have, and then we'll compare. So we're going to go ahead and put those, I'm going to put them in a whole new table, actually. So 183, oh, I guess I do have a little animation for part of them. So for unintentional entry and deployment, so for this category right here, my row total, 224 times 967, which is my column total, divided by 1580, works out to be 137.09. Okay, I already had this number from before. I just did this one. And again, I'm going to repeat the process. So for this guy right here, 1356 times 319 over 1580. Again, row total, column total, total. Okay, and that gives me 273.77. I know I just jumped through and added in a whole bunch, but again, repeat the process, row total, column total, divided by total, and you'll get the same expected values. If not, go back and double check your math, make sure you typed in everything into your calculator. So the whole point of finding my expected count was what? Finding out if I can even do a chi-squared test at all. Well, I look at my expected counts. They are all greater than 5, so I know that that condition is satisfied. So I'm going to check through my other conditions real quick. Let's see. So I was given a two-way table, was from my random sample. They gave me that, so we're good there. My sample was large enough to use a chi-square test since all my counts are greater than 5. And we are going to say that there's a population of at least 15,800 military personnel for independence. We can make that assumption. Okay, so now I need to find my chi-squared value. I have 6 different categories now because I have unintentional injury with deployed, unintentional with not deployed, illness, same thing, homicide or suicide, same thing. I have to find my chi-squared for all 6 of these values, okay, using the same chi-squared value that we had before. So again, I'm going to write out the first 2 and then the last one. And I'm going to do this for all 6. It doesn't matter necessarily what order, like do you have to go along the top and then do the ones at the bottom? Do you have to go down the row? It doesn't matter. As long as you have a couple of them at the beginning and then one on the end to show how you got your chi-squared value, that counts as showing your work. You're going to type this in your calculator, pause the video if you need to, or check to see what I have. And I have a chi-squared value of 51.9. To me, that seems kind of high, but that might not be depending on my degrees of freedom. Before, our degrees of freedom were, well, yeah, now we have too many things. We had, like before, our degrees of freedom was just 1 less than the total number of categories. Well, here it's not going to be quite the same because I have 3 different types of, well, in this, I have 3 different causes of death and 2 different causes, or 2 different deployment versus not deployment. So we are actually going to take 1 away from each. So to calculate my degrees of freedom, I had 3 over here and 2 over here. So I'm going to look at 2 less. So I say 2 less. Backtrack. I'm going to take my total, my row total. I had 2 rows. I'm going to subtract 1. I had 3 different columns. I'm going to subtract 1 and I multiply those together. So I have 1 times 2, which is 2. So I have 2 degrees of freedom. So with 2 degrees of freedom and a chi-squared value of 51.9 and an alpha of 0.05, okay, I'm going to look at my table, find my chi-squared value in the table is, oh wow, it's so far above this number that it's practically 0. So if that's the case, you have a teeny tiny p-value that's so small your table's like, nah, it's less than 0.005 by a landslide. If that is the case, that is definitely less than our alpha of 0.05, so we will reject our null hypothesis because our p-value is so small. There's enough evidence to believe the cause of death depends on deployment status. So this was a chi-squared test for independence. Watch the next video for a chi-squared test for homogeneity. You will compare the two. This one will always be used for a single population, but that has multiple categories in terms, it has a 2-way table for your categories. The M&M situation was a 1-way table. It had multiple categories. Those were our colors. But in this case, we just have, we have the one population, but we have both deployment status and cause of death. So we have, since it's 2-way, it's going to be require this test instead.